Hey guys, Pankaj here. Welcome back. So in today's statistics topic, we are going to cover what is Gaussian normal distribution and what are the different rules behind this. Okay, so we'll see empirical rule as well as Chebyshev theorem. Okay, so it's completely going to be theory, but yeah, it is remember that it is going to be very helpful whenever you are going to do statistical analysis for any given data. Okay, so let me share my desktop. Okay, so here is a topic which I'm going to cover. Empirical rule we'll see, and one example with the empirical rule so that you can easily understand the theory part, and similarly one Chebyshev theorem, and along with that some example. Okay, so what exactly? Let me just open the whiteboard and directly jump to the curve where empirical rule is going to be applied. Okay, so let's say you have a given data set whose values are normally distributed. So whenever you say values are normally distributed, right, it is going to exactly follow the bell curve. So how the bell curve looks like this, right? So whenever you say it is normally distributed, it is going to follow a couple of properties. Okay, so first property says that your mu, that is nothing but the mean of data for a given sample or given population, is going to be 0, and standard deviation is going to be 1. That is what is the first rule. Okay, so let's go ahead and draw mu where it is going to fall, mu 0, and your standard deviation is 1, right? So all your data set which is falling, so let's say this is mu 1 mu, then this is 2 mu, that is 2 standard deviation, this is third standard deviation. Okay, now let's follow the same thing on the other side because it is going to be symmetric, right? So here 1 sigma, then this is minus 2 sigma, and this is minus 3 sigma. Okay, so, and this is your x-axis and this is your y-axis. Fine. Now other rule says that whenever you have any data which is normally distributed, right, so definitely mu is going to be 0 and sigma, that is standard deviation, is going to be 1, right? So the data which falls between mu plus minus 1 sigma, right, all your 68% data is going to be covered under this. Okay, let me check, it is 65 or 68. It is going to be 68%. Okay, that's what this rule says. So that's why I'm telling this rule is very important, because if you know this theory, right, you can easily tell how your data looks like and what kind of percentage of data is falling within 1 sigma, 2 sigma, 3 sigma. Okay, that is second rule. And third rule, second rule, it says, the second is this one. Third rule is mu plus minus 2 sigma, means from here to here it is going to be covering how much data. Let me use another color here. So along with green, it is going to cover close to 95% of data. 95% of data will be covered between mu plus minus 2 sigma, and 68% data will be mu plus minus 1 sigma. And the fourth rule says if it is going to be mu plus minus 3 sigma, almost 99.7% data is covered under that. Okay, right from here. So just by looking the bell curve, if and only if your data is following the Gaussian normal distribution, this is what to be going to be applied in that data set. Okay, so definitely let me reiterate once again. Gaussian normal distribution, this is as per empirical theory, empirical rule, I would say. So empirical rule says whenever your data is normally distributed, it is then Gaussian normal distributed, then it is going to have mu, that is mean of the whole data set for population or the sample, going to be 0, and standard deviation of population sample is going to be 1. That is first rule. Second rule, all your 68% data will fall or lie between mu, that is mean plus minus 1 standard deviation. 95% of data will lie between mu plus minus 2 sigma, and 99.7% data will lie between mu plus minus 3 sigma. That is what your empirical rule says. Okay, so if you got this rule properly, then I'll solve an example, and with the help of example you can easily see like how you can infer the data. Okay, so this is the rule. Okay, whatever I just explained, same thing is written in this form. Now let's talk about the example. We'll take one example and just solve it based on the empirical rule. Okay, so what it is telling, heights of 18-year-old males have a bell-shaped distribution. They have already declared it is bell-shaped. Okay, means it is following the Gaussian normal distribution. Okay, but here they are telling mu is 69.6 inches and standard deviation is 1.4. So now by knowing those two values, you can infer a lot of data from the bell curve. Okay, so what they're telling, okay, so let me write here mu equal to what they're telling 69.6, right? So let's go ahead and write 69.6 and standard deviation is 1.4, right? 1.4. So let's go ahead and draw the data. So since they are already telling it is exactly following the bell curve, right? I'm just going to draw bell curve. And mu, they are already telling it is at 69.6. So let's go ahead and draw. And mu is 1.4. That is your 1 mu. And this is, let's say, 2 mu. And this is 3 mu. Similarly, other side also will draw -1, -2 mu, and -3 mu. Let's quickly calculate the value. So for 1 mu, what we have to do? Mu plus minus 1 mu equal to 69.6 plus 1.4. So 71.0, right? So this one mu will be 71.0. Okay. Similarly, 2 mu, so it will be just adding 1.4. So this will be your 72.4. 72.4, and this will be your 73.4. Okay, similarly other side 69.6 minus 1.4, 2, 8 and 6, just write 68.2. this is your minus. Okay, minus, yeah, you can write that, and 2 sigma, right? So 2 sigma, again 68 minus 2 minus 1.4, so this will be 8, then 716, 66.8. Okay, now one more time, 4615, 65.4, 65.4. Okay, so, and this is not going to be negative because 69.6 is a bigger value, right? So we are subtracting from that, this will be positive only, but this falls on the other side. Okay, so after drawing this, let me just draw the coverage. So now we have mu and 1 sigma, mu, 1 sigma, 2 sigma, 3 sigma, similarly minus 3 sigma, minus 2 sigma, minus 1 sigma. Okay, so this is your x-axis and this is your y-axis. Now let's go ahead and see what they're asking. So they're telling about what proportion of all such men are between 68.2 and 71 inches tall. So they're asking how many such persons are falling between 68.2 and 71 inches. So where is your 68.2? This is this one, and 71.0, right? So this is coming under what? Mu plus minus 1 sigma, correct? So I can clearly say, if as per Gaussian normal distribution, 68% data falls from mu plus minus 1 sigma. Okay, and 95% data falls from mu plus minus 2 sigma, and 99.7% value falls mu plus minus 3 sigma, right? So now you got the answer, right? You already know the empirical rule. So between this falls under -1 sigma to +1 sigma, right? So I can say 68% data or 68% population or 68% sample fall between 68.2 to 71.0. Okay, what exactly it means? Basically, the height of male between 68.2 to 71.0, there are 68% male candidate or female, whichever data has been collected, right? 68% data falls in that particular height. Okay. So this power outage. So this part is clear, right? Now let's go ahead and understand the other part. So what they're asking now, they're asking what interval centered on the mean should contain about 95% of all such mean. Okay, so this is the beauty of standard deviation, right? They are telling the total quantity, right? So that's what they're asking, total proportion or total quantity. So they are asking now what interval centered on the mean should contain about 95% of all such mean. Okay, so as per empirical rule, let me write here empirical rule. 95% falls between mu plus minus 2 sigma. Okay, so let's go ahead and draw mu plus minus 2 sigma. So mu plus minus 2 sigma is from here to here. This portion is also coming. So let me just draw. So from where to where? Basically, 95% of male candidates are between 66.8. It is not writing. 95% of population or sample are falling between 66.8 to where 72.4. 72.4. That is what is the answer for next question. Okay, so that is the answer which they are falling under 95%. So guys, see how simple it is. If you understand the empirical rule, just by having mu and sigma or the mean and the standard deviation, you can infer a lot of data. Okay, so these kind of examples or these kind of statistical what do you say if you want to infer some kind of internal information from the data or to get more insight about the data, you just have to know mu and sigma, that is mean and standard deviation, and you can infer a lot of insights about the data. Okay, so this will be very helpful. Let's say when you are collecting, let's say some companies ordering t-shirt for the employee, right? So they would like to understand which particular size of the t-shirt should be ordered, right? How many such t-shirts should be ordered so that majority of the population or majority of the sample is covered, right? So they will just calculate, they will have some sample data collected, sample heights from the employee. Okay, and based on that they can infer a lot of figure or a lot of number, like only let's say if I order these many t-shirts, right, this is going to cover maybe 1,000 employee or 2,000 employees, right? Just by having mu and sigma. Okay, so not only for this kind of collection, so many other different kind of data collection also, it will be helpful when you have this empirical one. Okay, so there is a limitation for empirical load. Your data must be following the bell curve. Okay, that's what is Gaussian normal distribution is telling. But what about data which is not following the Gaussian distribution? Okay, that's where your Chebyshev theorem comes into picture. Okay, so let's see what Chebyshev theorem is telling. The empirical rule does not apply to all dataset, only to those that are bell-shaped. That's what we saw just now. Okay, and even then it is stated in the approximation. So those are whatever we just said, those are approximate, not the exact value or hard-coded value. Okay, so a result that applies to every data set is known as Chebyshev theorem. So let's see what they are doing. They are telling at least 3/4 of the data lie within 2 standard deviation of the mean. That is the interval within x minus, this is nothing but your mean. Okay, so I'll just remove it, mean. While adding this data, this bar is coming as minus, so let me remove this part. Assume that that is mean. Okay, so 3/4 of the data falls between mu plus minus 2 sigma, and 8/9 of data lies between x plus minus 3 sigma. Okay, and at least 1 minus 1 upon k square of the data lie within k standard deviation. So we were seeing like 1 is standard, 2 standard, 3 standard. So whatever other standard deviation you would like to calculate, so k is the value here. Okay, k is the parameter which you can choose based on the mean. So k standard deviation of the mean, that is in the interval with endpoints x plus minus ks for samples, and the endpoint mu plus minus k sigma, that is for sample and as well as population. where k is the any positive whole number that is greater than 1. Okay, so if any data which is not following the Gaussian curve or the bell curve, it is going to be looking like this. It may be different kind of shape, but it will not be exactly bell curve. So when you don't have exactly bell curve, this is the rule to be followed. Okay, so let me just explain once again. So I'll just erase this, or maybe I'll take another sheet here. Where it is, whiteboard. Okay, so let me just again draw the data. So you have any data. So what they're telling, Chebyshev theorem. Okay, data which is not following bell curve. So basically, this Chebyshev theorem can be applied to any data, either it is following bell curve or not bell curve. Okay, so this is a standard what to say theory. So let's say those data which is not following, it may look like this, correct? Or maybe some data may look like this, correct? And some data may look like this. Any kind of data, correct? So let me just draw one sample here. This is your data. Okay, let's say your mean is falling somewhere here. Okay, this is your mean, and they are telling if I take 1 sigma, this is, I take 2 sigma, this will be 3 sigma. Similarly, other side, -1, -2, and this is your -3 sigma. So what they are telling, as per this theory, 3/4 of data will fall from mu plus minus 2 sigma. Okay, so 3/4 of data, if you just talk about this, right, this is your 3/4 data. 3/4 of data falls mu plus minus 2 sigma. Okay, that is what the first part of theory tells. Now if you talk about 8/9 of data, 8/9 of data falls between mu plus minus 3 sigma, means from here to here, that data falls between mu plus minus 3 sigma. Okay, 8/9 of data. And if you would like to calculate, like at this particular standard deviation, how much such data falls, right? So for that, they are telling at kth standard deviation, 1 minus 1 upon k square, this much data will be falling. Okay, so where k is your standard deviation, which is greater than or equal to 1, any whole number. Okay, any integer number. Okay, so that is what is your Chebyshev theorem. So let's talk about this example and see how we can calculate it. Okay, so they're telling a sample size of n equal to 50, mean equal to 28, and a standard deviation is equal to 3. Without knowing anything else about the sample, what can be said about the number of observations that lie in interval between 22 to 34? What can be said about the number of observations that lie outside the interval? Okay, so we are going to solve it, but just remember, guys, whatever theory says, right, it is telling at least that much data will be definitely. It is also approximation, right? It is not exactly hard coded. At least 3/4 of the data will fall in that. Okay, and at most 1/4 of the data fall into that. So at least 3/4 data will be coming to mu plus minus 2 sigma. So let's solve this particular problem and understand the theory. So they are giving mu equal to 28. So I'm just going to take this data once again. Let's say some data is there. Here is your mu equal to 28, and they are telling sigma equal to 3. So mu equal to 28, sigma equal to 3, and that is number of population or sample, let's say 50. Okay, and what they're asking, 22 and 34, right? So let's say 1 sigma will be coming, let's say mu plus minus 1 sigma is 28 plus 3, right? So 8, 9, 10, 11. So it will be 31. Okay, so let me write 28. This will be 31, and 2 sigma will be 34, and 3 sigma will be 37. Okay, similarly here, take minus 1 sigma. So 28 minus 3, that is 25. Then this will be your 22, and this will be your 19. Okay, now let's take another color. So what they're telling, between 22 to 34, let me reconfirm, 22 to 34, correct? Between this, what can be said about the number of observations that lie outside the interval? Okay, so again, read this once again. What can be said about the number of observations that lie in the interval 22 to 34? Okay, so 22 to 34, what we have here, 22 to 34. So they are telling at least, right? So at least 3/4 of data will be falling from mu plus minus 2 sigma 3/4 of data. So 3 by 4 into, what is the sample? 50, right? So total how much? So this will be 150 by 4. So 3, then 28, right? So 37.5. So 37.5 data, 37.5 population, or the height, or whatever they are collecting, right? That will be falling from what do you say, mu plus minus 2 sigma 3/4 of data, that is 37.5. This is the answer for this particular thing. Okay, so that's what they're asking. So what can be said about the number of observations? So 37.5 observations. So remember, guys, this will be whole number, right? So we cannot just take the float number of this. So I should say here 38 observations are falling from mu plus minus 2 sigma, whose height is equal to 22 to 34. Okay, that's what they're telling. Okay, so what about next? What can be said about the number of observations that lie outside the interval? So what do you mean by outside? So as per Chebyshev theorem, what they're telling, it should be at least, right? So at most those will be outside. So what I can do? So outside will be looking like this. So here, this will be your inside. Okay, outside, whatever is falling, that is something will be like this. Okay, so 3/4 will be inside, then outside will be your 1 minus 3 by 4, that is 1 by 4. So 1/4 of data. So 1/4 multiplied by 50. So 50 by 4, how much? 4, that is, and here 1, that is 2, then let's say 5. So 12.5, that is, again, we can take the integer value only, right? So close to 13 observation will be falling outside mu plus minus 2 sigma. That will be outside. Inside we already saw that is 3/4. So outside 13 observation will be falling somewhere here. That's what about the outside data. Okay, so that's how guys, we calculate the observation just by having standard deviation as well as mean. No matter your Gaussian distribution data or any data which is not following the Gaussian curve or not following the bell curve, Chebyshev theorem will help you to get the insight about the data, as long as you have mu and sigma or standard deviation and the mean. Okay, so that is the way you solve the problem. And here, this library is now not required. It is just to understand the theory about empirical rule as well as Chebyshev theorem with the help of some example. Okay, so that's all from my side. I'll be uploading this notebook in the Google Drive, Jovian, as well as GitHub. Please download and read about it, and try something. Take some data, either from Iris load dataset or from different dataset, or maybe any external data, and just try something. Okay, so you will find a lot of examples like this, and just by having mu and sigma, you can solve the problem. It's very easy to solve. Okay, guys, so that's all. And in the next video, we'll be talking about a couple of more rules in the statistics with some formula and example. Okay. So stay tuned and see you in the next video. Thank you. Bye bye.